Section 11.2.13. The manufacturer of hardness testing equipment uses steel ball indenters to penetrate metal that is being tested. However, the manufacturer thinks it would be better to use a diamond indenter so that all types of metal can be tested. Because of differences between the two types of indenters, it is suspected that the two methods will produce different hardness readings. The metal specimens to be tested are large enough so that two indentions can be made. Therefore, the manufacturer uses both indenters on each specimen and compares the hardness readings. We want to be able to construct a 95% confidence interval to judge whether the two indenters result in different measurements. Now, note here it says a normal probability plot and a box plot of the data indicate that the differences are approximately normally distributed with no outliers. So we don't need to confirm that since it's already given to us. So here is the data. Here we have specimen goes from 1 to 9. So we have 9, which is the sample size. We have the steel ball for the first part and then a diamond for the second. Okay, now what we want to be able to do is we want to be able to construct a 95% confidence interval to judge whether the two indenters result in different measurements, where the differences are computed as diamond minus steel ball. A 1 minus alpha times 100% confidence interval for the mean differences is given by the formulas below. Here is the lower bound and there is the upper bound. Now, to state the appropriate conclusion, we're going to determine whether the confidence interval includes 0. If the confidence interval does not include 0, there is sufficient evidence to conclude that the two indenters produce different hardness readings. Otherwise, there is insufficient evidence to conclude that the two indenters produce different hardness readings. Okay, so we need to find the difference between the diamond and the steel. So we're going to create another row here, and so we're looking for the difference. So that means we're taking a diamond, as you can see here, minus the steel ball. So we're going to take 54, and then we're going to subtract 52 to get 2. And then here we're going to take 55 and then subtract 57 to get negative 2. We're going to take 61 and then 62, subtract 61 to get 1. We're going to take 74, subtract 72 to get 2. We're going to take 69 and subtract 68 to get 1. We get 57 minus 54, which gives us 3. 68 minus 65, which also gives us 3. 51 minus 51, which is 0, and then 56 minus 53, which is equal to 3. Okay, so now what we have is we have the differences. And so the differences, we want to be able to then find out what is the mean, what is the standard deviation of those differences. So what we want to do is we want to be able to find the following. So in step 1, we want to be able to find what is the mean of the differences. We want to be able to find the standard deviation of the differences. We also want to know what the sample size is. Well, the sample size is given up here because we have 9 samples. So we know n is equal to 9. And then we also need to find the critical t value of this particular problem so we can plug it in. So before we want to be able to find the critical t value, let's go ahead and find the mean differences in the standard deviation. So I'm going to open this up in StatCrunch. So you can see here's our data. We can go ahead and open this data up into StatCrunch. Okay, and then we're going to create a column here. We're going to call it difference. Okay, and then we're going to put in the values. So we know the difference is going to be 2, negative 2, 1, 2, 1, 3, 3, 0, and then 3. And so what we want to be able to do is we want to be able to find the mean of this column and the standard deviation. So we're going to go ahead and go to Stat, go to Summary Stats, and we're going to go to Columns. We're going to select the difference column that we created, and we want the mean and the standard deviation. So let's go ahead and compute. Okay, so here is our mean and our standard deviation. So the mean, if we run it to one decimal place, is going to be 1.4. And the standard deviation, if we run it to one decimal place, is going to be 1.7. Okay, so now what we know is we know that we have the sample size, the standard deviation of differences, and the mean. Now we need to find the critical value, okay, which is the critical t-value. Well, the first thing we need to know is what is alpha? Well, since we're constructing a 95% confidence interval, we're going to take 1 and then subtract 0.95, which is going to give us 0.05. And then we need to take that alpha and then we need to divide it by 2. So if we take that 0.05 and then divide that by 2, well, that's going to give us 0.025. So therefore, there is the area that we need. Now we need to also find the degrees of freedom. Degrees of freedom is taking a sample size and subtracting 1. We know that's 9 minus 1, which is going to give us 8. So now we have the degrees of freedom. Okay, so let's take a look at our table here. We know that we have an area of 0.025. We know the degrees of freedom is 8. So we'll be able to determine what is the critical value there. And so there is the critical value. So the critical value of t at the area of 0.025 is equal to 2.306. Okay, so now what we need to do is we need to find the lower bound using the lower bound formula and the upper bound as well. Okay, so let's go ahead and then find the lower bound. Well, the lower bound is going to equal the mean, which is 1.4. We're going to subtract the critical value, which is 2.306. We're going to multiply it by the standard deviation, which is 1.7, divided by the square root of 3. Okay, so let's go ahead and determine what is the lower bound here. Okay, so we're going to do this order of operations. So we have negative, okay, so it's negative, and that's parentheses 2.306 times 1.7. And then we're going to divide that by the square root of not 3. Let me go ahead and correct that. That should be the square root of 9. Which gives you the value of 3. So we can divide this by 3. And then we're going to add the 1.4. So plus 1.4. Okay, so therefore there is our result. Okay, now they want us to round this to one decimal place for this particular problem, so we're going to approximate this to be 0.1. Okay, now we need to find the upper bound. Okay, so if we want to find the upper bound, we're going to use the following formula. So it's going to be almost similar to what we have here. The only thing is now instead of subtracting, we are going to add. So let's go ahead and determine what the upper bound is by using our calculator here. So again, we have 2.306, multiply that by the standard deviation of 1.7, and then we're going to divide that by the square root of 9, which is 3, and now we're going to add 1.4. So therefore there is our result. So now we're going to round this to one decimal place. So we end up getting 2.7. So we know what our lower bound is, we know what our upper bound is. So when we look at the confidence interval, we have our confidence interval where the lower bound is 0.1 and the upper bound is 2.7. Okay, so let's go ahead and go back to the beginning here where it says to state the appropriate conclusion, determine whether the confidence interval includes 0. If the confidence interval does not include 0, there is sufficient evidence to conclude that the two indenters produce different hardness readings. Otherwise, there is insufficient evidence to conclude that the two indenters produce different hardness readings. If you look at this interval, 0 is not included. So since the confidence interval does not include 0, we can say that there is sufficient evidence to conclude that the two indenters produce different hardness readings.